Okay, thank you. Thank you, Matteo, for the kind introduction. Yeah, as you said, I'm going to talk about basically the recent work that we have done in my lab, but more focus on the energy side. So in my lab, we really work in two very different domains, on the energy side and the healthcare side, but I'm going to focus most on the energy side, as I said. So basically, let me see if this works. You can see my pointer, right? Okay. Yeah. So this is the first slide that I generally use to explain a little bit of the motivation behind the research we do. Okay, as I said, we work on healthcare and energy areas, but basically this really illustrates why we do what we do. What we have here is the projections of the population growth, and I have included here the billions of people living as a function of the years, and I have highlighted here also two important dates. The first one is the end of the Second World War, and at this point you could see a huge increase in the population growth, probably as a result of the development of antibiotics, vaccines, but also advances with food production. This is where we are now, and we have here also these three different projections. The more realistic one is probably this orange one that suggests that we will end up this century, the 21st century, with about 10 billion people living on the Earth. And therefore, we are going to face very important challenges. This includes the exploitation of natural resources, water, okay, sweet water, drinking water, access to healthcare, cheap healthcare, something particularly important these days with COVID-19, but obviously also beyond that. Food demand is going to be very important if we are going to have 10 billion of people living on the Earth, and obviously everything that is related with energy and pollution is going to be also extremely important. The same idea is summarized in this slide. Here you have the 21st century global challenges, and I have highlighted a few ones where my lab is really working, including the healthcare, as I said, which is something I'm not going to cover today, water harvesting, water purification, but also with energy, hydrogen storage, carbon capture, heating, air conditioning, all these different ideas that are extremely important for this challenge. And there is also some importance. I mean, Matteo, in the introduction, you were saying, yeah, we work with some petrochemical companies, and this is the perception we really have about all these companies, right? We talk about this all chemical engineering and the exploitation of fossil fuels and all the impact we have into the global warming. It's quite important also to highlight some of the challenges that we have been facing in the past centuries. In the 18th century, we started using a solid fuel, okay, coal for the Industrial Revolution. That was extremely important to be able to get a lot of energy very quickly. In the 19th century, we started moving to a liquid fossil fuel, petroleum, which is much more flexible. We can do many ideas that with coal, with a solid fuel, was almost impossible, okay, especially not only just consuming energy, but also with all the polymer industry. And in the 20th century, we moved to the exploitation of natural gas, so from a solid, a liquid, and a gas. And we are talking about the future economy of hydrogen these days, right? With renewable energies, basically being able to solve a lot of the challenges that we had with these previous fossil fuels. And this is quite important because I need to highlight, obviously, that the challenges that are associated with a solid, a liquid, and a gas are going to be very different. And we had a lot of technologies that were able to deal with solids, liquids, but with gases, probably we will need to have some new ideas. And this is why porous materials are going to be important. This is why metalorganic frameworks, which is some of the materials we work with, are going to be critical. And all in all, we want to move from this all chemical engineering perspective into this new science where we exploit development in nanotechnology, in green chemistry, in computational techniques, including machine learning, in order to create advanced materials that will allow us to solve all these challenges that I was talking before. Okay. Just to give a little bit of an overview of the work we do in my lab, we work with nanoporous materials. We call these nanoporous materials of the 21st century. We have been working with activated carbons a little bit, okay, fancy activated carbons, with zeolites, really interesting materials for industry, mesoporous silicas a little bit. We mostly focus on the use of metalorganic frameworks, porous coordination polymers, and similar materials. Okay, the definition of this name is just a little bit of a random name, metalorganic frameworks. Basically, a lot of different ideas about this coordination chemistry and the exploitation of the porosity of all these different structures. And all in all, what I also want to have is to be able to understand all the physical chemistry which is involved in the absorption phenomena. And if we are really able to understand what is really happening with all these porous materials and the gases or liquids that are getting absorbed, we should be able to apply them to solve specific questions in industrial applications. Okay, this is basically what we want to do, develop all these core fundamental ideas to be able to explain what is going to, what can we do to improve all the industrial application and all the challenges related to that. The approach we follow in my lab has three main legs. The first one is the use of computational modeling. We use a lot of classical simulation, including Monte Carlo, molecular dynamics. We move a little bit onto process modeling and machine learning these days, which is very important. We use all these different ideas to try to screen structures, databases with materials. We select the best ones, and then we go to the lab. We try to do the synthesis, well, we do the synthesis of the best materials that we have identified in this process, and we pay attention not only to the synthesis of the materials, but also to the shaping of these structures into something that we call monolithic materials, which is something I will talk later today. All this involves the engineering of the materials. It's not only about the shaping, but also about the scale up and the process optimization. Okay, all these loops to the first modeling step, and basically we have a feedback of all these different legs that we have in my lab, trying to improve the way we advance all these different materials. So, what is a MOF? You probably know what is a MOF, but this is also the generic slide I use to introduce these materials in case one of you don't know too much about these porous materials, but basically they could be defined like porous coordination polymers. They created by the self-assembly of metallic clusters and organic ligands, all these different building blocks rearranged, and then we have three-dimensional, two-dimensional materials where we can really exploit the porosity, which is all the space between all these different building blocks that we have. The first time that the MOF name was included in a paper that was from Professor Diaghi in the US, but at the same time, earlier than that, there was the work from Robson, for example, and many others working on similar areas, trying to say, well, we can really create all these different scaffolds, and in theory, we should be able to exploit all the porosity of these materials. So this really goes into the shoulders of the giants, and if we look at the literature and the work that has been done previously. Why these materials are important? Very precise control over the structures. If these materials are crystalline, we can really define the different building blocks, and we are going to be able to control the properties of all these different structures. And this is quite important. We can also have, in some materials, at least extremely high pore volumes and surface areas. Sometimes we talk about several thousands of square meters per gram. We can also play easily with the pore size of the materials just by choosing the different building blocks. If we have a longer organic molecule, we will be able to have larger porosity. And we can also modify this after the synthesis. At the end of the day, there are thousands of materials, thousands of structures that can work in many applications. So this is great. We can do this with zeolites. Well, we have 250 zeolites, activated carbons. Yeah, we have a lot of different materials, but crystalline structures, thousands of structures for any application. I mean, this is a particular strong point of metalorganic frameworks. But these materials are not perfect. Okay, like anything, we also suffer about some issues, such as, for example, low mechanical and thermochemical stability, which is something we need to pay a lot of attention. Low density, okay, we are talking about materials with extremely high pore volumes, then we are also going to have really, really low density materials. And this is a problem, okay? We don't want to have low density materials. We want to have high porosities, high surface areas, but also high densities, because the volumetric capacity, which is the amount of material I can really put in a specific volume, like this bottle I have here, is going to be defined by the density of the structure. And there is another problem. Yeah, there are thousands of materials. So how I'm going to filter, how I'm going to choose the best material for the application I'm looking for. I said these MOFs are crystallines, and this is really good news because we can use computational methods to help us answering this question. Okay, I have highlighted two main questions in this presentation. The first one is, can we find a deterministic prediction for materials performance? Can I really, if we understand how these materials are made of, if we understand the building blocks,
sorry, David. I don't know. I can't hear you anymore. I think you muted yourself.
Okay. Can you hear me?
Now.
Can you hear me now?
Now I can hear you, yeah.
Okay, it was muted. I don't know why. Okay, so basically, I'm just trying to find an answer for these two questions, okay? The deterministic prediction for materials performance, okay? If I really know the building blocks of the structures, can I really know how the materials are going to perform? And the second one is, can I really have these predictions translated into real materials, okay? I don't want to have just the computational simulation. I really want to have something which is real. So this is how the MOFs look under the microscope. This is a beautiful image of SEM data for a material called C8, Zeolitic Imidazollate Framework number 8. And you can see the beautiful crystallites, in this case is micron size structures, really, really beautiful. And the beauty of all these materials is that we can really condense gas molecules, we can concentrate them inside the porosity. And if we have two different components, we can really flow this through the porous material, and we will be able to select one of the gases and not the other one. So we can really separate molecules if we want. Thinking about absorption and the concentration of molecules, we have, for example, the storage of natural gas, right? I was talking about the challenges that I was having when dealing with gases. I cannot use very high pressure. Okay, I can use high pressure and store the natural gas, which is basically methane, inside one tank. Or I have also another possibility, which is to take the same tank and fill this with a porous material. So where am I going to have a higher amount of gas? Well, if I want to have exactly the same amount of fuel, then in the empty tank, I need to go to extremely high pressures, 250 bar. But if I want to have the same amount of fuel, I just need to use a fraction of the pressure in the porous material tank. Okay, you can also see this in this cartoon. These walls are extremely thick, but here this is very thin, just basically because the pressure is lower. So this is going to be lighter, probably it's going to be safer, it's going to be cheaper. This is basically the idea that we have behind all these different porous materials. And what you can see here in the slide is a monolithic metalorganic framework. This is the C8. This is exactly the same material I was talking before with the SEM, the beautiful image about these structures. And it's not a powder, it's a monolith. Okay, this is about the engineering of these structures. You can see they look very transparent, okay, almost glassy material, but these are fully crystalline. And we can use different MOFs for all the different applications I mentioned. Okay, we can really have gas separation, gas storage, drug delivery applications in healthcare. Okay, something that we pay quite a lot of attention. We can also apply this for sensing applications. We can apply this for energy production, catalysis. Okay, a lot of different possibilities in all these different structures. And what MOF? For what application? This is the big question, right? These deterministic predictions of the material's performance. This is something I wanted to do. This is the number of structures that have been published in the literature, any crystalline material, as a function of the year. Okay, all this data is basically stored in an institute that is in Cambridge, the Cambridge Crystallographic Database Center. You probably know, and basically they were quite happy because a few years ago they were able to get 1 million entries in this database. They have been from the early 70s curating all the crystalline materials that are published, and they were coming to us and ask, how many MOFs do we have in our database? And we said, well, you know, this question has been asked before, and there's a couple of databases existing already. And one of the best examples, not the first and not the only example, but this is one paper that was published in 2014 from Professor David Soul and Randall Snar. And basically they were saying, well, We have 5,000 different materials. Okay, we call this the core MOF database. And we said, well, we think the number is much higher. They knew the paper, obviously, but they wanted to have their own data set. And they were asking, how many MOFs do we have? Okay, how many MOFs have been synthesized so far? They were also asking, well, do you know how many MOFs can really be synthesized in the future as well? And the questions we were having from our side was, can we also predict the performance of these materials using molecular simulation? And also this question about, is there any optimum structure for a given application? Okay, all this is about using computational chemistry to really be able to screen porous materials. We were working with the CCDC, the Cambridge Structural Database Center. Everything that I'm going to describe here is basically described in this tutorial that we published last year. And basically, we were using Conquest. This is the tool from the CCDC. And we were taking one MOF, a prototypical structure. This is MOF 5. The gray sphere is representing the porosity of the material. This is the metal cluster, the organic ligand. And we use Conquest to transform this structure, this idea, into this diagram that you can see here. Okay, this is basically drawing the metal cluster, the organic ligand, metal cluster, and so on. It's a zinc oxide cluster. This is transformed into this criterion that you can see here on the left. This is using Conquest tools. And we can continue with all these different ideas. So we have one criterion, but we can really grow this into multiple different criteria. And what we did in this first publication, when we published the database of MOFs in the CCDC, we were including all these different criteria that you can really see in the screen. And all this was trying to make sure that we were including all the metalorganic frameworks that we knew existed, and really trying to see and try to challenge ourselves, try to find if we were missing any other structures or if we were including any false positives. At the end of the day, all this is very flexible. All this can really be modified as soon as we want. So this is important because if we find that these criteria are not enough, we can easily modify them. We can extend them, and we can really try to take into account any new structures and new ideas that are created. We published the first paper, but we had also a follow-up last year that we published in Chemical Science. And basically, we were trying to create different families of materials. So we were trying to pay attention to specific families that we were aware of and we were interested. But again, this is very flexible. So if someone has any family of materials that they are interested, this is very easy to go to and try to modify all the criteria that are used and very well described in these structures, in these papers. This is for zirconium MOFs, very good because they have very high stability. This is for CPO27, MOF74 like materials, really important because of the existence of open metal sites. We have also zeolitic imidazolate frameworks. We have these iron MOF-like materials, zinc oxide structures. We have also copper-copper paddle wheel metalorganic frameworks. Any family of materials, if something is not included here, that's not a problem because you can really go to the Conquest, the program from the CCDC, and you can really start defining your own databases, your own structures. As I said, very, very flexible. This is the first paper that we published on this collection of structures, and this is for, we say, for the past, present, and future, because this is a curated database. This means that when we published the paper, there were about 70,000 different materials, but automatically, about 4 times per year, this database is updated by the CCDC, just taking into account the criteria we were defining. Today, we have about 100,000 different materials, and porous materials are about 10 or 15% of these structures. So a lot of successful results from this database. This is important because now, once we have a database, we can start using molecular simulations to predict the structures of all these different materials. What is this molecular simulation about? All this is trying to answer these what-if scenarios. So at the end of the day, we can use Monte Carlo techniques to be able to answer the question of, if I have a material and I have this pressure and temperature and this component, like methane or hydrogen, how much gas is going to be absorbed in the material in these conditions? If I have a mix of different gases, what is going to be the selectivity of this material that I'm producing? The input information we need, what is more important, is the crystalline structure of the metalorganic frameworks of these materials. And because we have the database, we can really screen hundreds of thousands of materials if we want to for all these gas absorption applications or any other applications that we have. Monte Carlo, how much? Molecular dynamics, how fast the molecules get absorbed. Okay, how fast they diffuse through the porous network. And what is also very important and very different from quantum mechanics, for example, is that we get data that we can compare face to face with experiments. It's exactly the same information. You will see this in the next slides as an example. We can also get a very detailed picture of the absorption process on a molecular level, and this could be also very, very helpful. This can also help us to define better materials. How does it work, these molecular simulations, and does it work? This is an example with NU100, a material from Northwestern University. This is the metal cluster, and this is the organic ligand. And in purple, you can see the porosity of the material. Okay, the NU100 has 3 different cavities, small one, medium, and a big mesoporous cavity here. We can run molecular simulations, as I said. We just take the structure of the material as an input file, and we can simulate the performance for hydrogen storage at 77 Kelvin. This is the uptake of hydrogen per gram of material when I increase the pressure. This is the absolute capacity, the excess capacity. In black is the experiment without looking at the simulations, and in red is the simulation, again, without looking to the experimental data. The simulation is not a match, it's not a fitting of the experimental data using Langmuir equation or anything like that. It's basically ignoring anything from the experiments apart from the structure of the material and just using statistical methods to be able to predict the performance of the structure. So really, really good agreement. And this means that if we can do this for one single structure, we can obviously take a whole database of materials and start running all the simulations in parallel. And this is basically what is shown in this slide. Every single point you see here is the result of one molecular simulation, 16,000 different points, different metalorganic frameworks for hydrogen storage at low temperature, but not cryogenic temperature. You can see MOFs that perform extremely well, MOFs that perform not that well, and you can also see all the different components. So we take all these different ideas and we can also extend this for different conditions. What if we go for room temperature? We can also do that. And we can also show all this different information. Every single point again here is one different metalorganic framework. All this information is also now taken into account not only characteristics about pore volume or surface area, but also we can split this into the different families that we were identifying before in the database. We have these zeolitic imidazolitic framework materials or zirconium MOFs that we know are particularly robust and so on. The size of the symbol is related with the size of the cavities, and this allows us to really explore all the physical limits that exist in one specific application in gas storage. We can do this also looking at the percolation theory. So it's the way that the network is interconnected. If we have one-dimensional channels or three-dimensional networks, we can have very, very good description of what is really happening at different pressures as well, 200, 500, 900 bar. And we can identify the top material, which is this one that you can really see here in the screen. We can also apply some statistical information, try to really understand the dispersibility of the data. So this helps us to identify the best materials and the best families for specific applications if we want. Is a lot of knowledge that we can really take into account. Looking at the volumetric capacity and the percolation theory, if we have materials with one-dimensional channels, two-dimensional porosity, or three-dimensional network, you can see that on average, three-dimensional materials perform much better than one-dimensional structures. So if I need to choose one without knowing more information, I'm probably looking for three-dimensional networks in this application. Okay, this is an example of how this analysis, the statistical analysis and big data can help us to identify the best materials. This is for single components, basically the amount of hydrogen we can really store, or if you want, the working capacity. But when we are having mixtures, the situation is a little bit more complex. We need to pay attention to different parameters. We need to pay attention to these working capacities that I'm having described here. This is basically the difference of the amount of gas that is absorbed at high pressure minus the amount of gas that is absorbed at low pressure. And depending on the shape of the isotherm, this working capacity is going to be more important, it's going to be higher or lower. This is quite important. This is, as I said, this working capacity, but then we have other parameters that are also going to be extremely important for mixtures. In particular, the selectivity of a structure is going to be really, really important. The next slide is going to be about the separation, CO-nitrogen separation. Carbon monoxide and nitrogen, physically, they are very similar. Chemically, they are very different. We are trying to find the best material for this separation. We want to have a material that is able to absorb a lot of CO, yeah, but also a material that is highly selective for CO. And this is challenging. We also want to know how easy it is to regenerate the material. And all this basically start moving into the idea of the process simulations. We need to get more information about what kind of process we are going to use. Are we going to use a PSA, pressure temperature, pressure swing absorption? We are going to have TSA. What is the process that we are going to have in our simulations, in our industrial process? This is the data that we can collect for a specific family of materials. In this case, we were taking copper paddle wheel clusters. Typical material is HCUS1, but all the sister structures to this HCUS1 material. This is for PSA process, and you can see here the selectivity of CO versus nitrogen versus the working capacity. We want to have materials in this corner, materials with high working capacity. We absorb a lot of CO, we remove a lot of CO, but also very selective. We only want to do this with CO, not with nitrogen. And as you can imagine, this is very challenging, it's very difficult or almost impossible. If a material has very high selectivity, like this material here, it means that it's going to be very hungry for these CO molecules, and therefore it's going to be very difficult to remove them from the structure, and therefore the working capacity is going to be very low. And if a material has a high working capacity, it means it stores a lot of CO, it removes a lot of CO, but also the selectivity cannot be very, very high because this material is not going to be having that specific interactions. So this is a kind of a multivariable game where we really need to take into account all the different possibilities to define what is the best material. And this is something we really need to build. This is something we really need to understand. We have then a transformation into temperature swing absorption process. From the PSA, we move to the TSA, decreasing the temperature or increasing the temperature, and we can really have all these different values. But the key question here is that to choose the best material, the optimal material, we really need to use process simulations. We need to complicate the picture a little bit more. This is not under review anymore. This is something we published in Chemical Science this summer. So if you really want to expand this, everything is included there. And we pay quite a lot of attention, try to have something which is open enough for non-computational people. So if you are working on experiments, don't worry, because this would be relatively easy to read. And still a question I was trying to answer today was, can I find a deterministic prediction for the material's performance? Okay, if I really know the surface area of a material, the pore volume, the pore size, the density, the composition, the different building blocks, can I really map all the properties and I can really predict quickly what is going to be the performance of this structure? The key word here is deterministic. Monte Carlo simulations are fine, but not enough. But this is basically what I'm trying to show in the next couple of slides. This is for another application. This is for oxygen storage. Again, trying to explore what are the physical limits. And if I have the gravimetric capacity and volumetric capacity as a function of the interaction of the oxygen with the Metalorganic Framework, I have thousands, 3,000 of materials included in this slide. I can say, well, the optimal interaction needs to be between 10 and 15 kilojoules per mole, but at the same time, I have materials that perform extremely well and materials that do not perform very well. So how can I really improve that? The key question is that this is, again, a multidimensional problem. And I need to focus, I need to pay attention not only about the interaction, but also about the porosity of the materials. In this case, this is the void fraction, is how porous the material is. And we can find optimal values for interaction, but optimal values as well for the void fraction. In this material was about 0.9, if I remember correctly, for all this representation that I'm having here. We work with representations, obviously, in the papers, but we also want to have the opportunity of offering all these simulation capabilities to experimentalists, for example, that cannot really reproduce this data easily. And this is why we have created interactive websites to really explore all the data that we have been predicting in our publications. If you go to this database, to these websites, you will be able to see something very similar. You will see the actual example in the next slides, where you have one property on the y-axis, in this case, the volumetric capacity for oxygen storage. On the other one, you have the gravimetric capacity. This number is in gray, is the pressure that we are using for storing the oxygen. And every single sphere here is one metalorganic framework. If we increase the pressure, okay, this is the dynamic representation of all these different simulations that we are having. We increase the pressure, and you can see how the different materials start evolving in this process. You can see how the materials with lower void fractions and smaller sizes, they get stuck at lower uptakes. This is something you can imagine. Whereas all these purple materials, they really continue growing when we increase the pressure. We can also have not only two-dimensional representations, but and this is actual the MOF Explorer. This is the three-dimensional representation of this website. You can really play with all the data that we have. We can increase the pressure, decrease the pressure. We can really play on these, select materials, so we can really go and try to find the best materials for the specific application we are looking for. It's not only necessarily, or it's not necessarily the top material in terms of absorption performance, because we can also maybe would like to pay attention to another structure which has maybe lower capacity, but is going to be more robust. Okay, it's going to be more selective for that particular gas, or is something that is going to be cheaper, maybe because it's made with cheaper metals, cheaper building blocks. All these basically allow us to play with all the different properties of the materials. And what is also important is that you click on the structures that you find here, and you will see the original link from the Cambridge structural database. You can find these numbers, these names that you can see here. This directs you to the original paper, and you can see the original synthesis of all these different structures. So it's an extremely useful tool. We also prove that all the experiments are confirmed. All the simulations are confirmed with experiments. This is the nitrogen isotherm that we measured at 77 to evaluate the quality of the material. Nitrogen uptake as a function of the pressure, the simulation, and the experiments. You can see that we have really, really nice match here. This means that we are able to predict the quality of the structure. The quality of the structure experimentally is very, very good. And this means that the experimental data matches with what we were simulating. If we go for the oxygen storage, the real application, this is the amount of gas stored, cubic centimeters of oxygen per cubic centimeters of Metalorganic Framework when we increase the pressure. This is the comparison with an empty tank. This is the effect of compressing the oxygen inside the tank. This is the best material that was published in the literature, something called NU125. This is the best material that we identified in our screening, the simulation, and this is the best material experimentally studied. And you can see some deviations here, but at the end of the day, at high pressures, we have something which is really, really close to the molecular simulation. So perfect match, extremely happy with all these different results. Have I answered this question? I haven't. Can we find a deterministic prediction for materials performance? I haven't done that. Why? Because this is not only about Monte Carlo simulations. We need to go beyond that. But something before I really jump into try to answer this question. This is another effort that we did to characterize the materials. And this is going to be important because if we want to compare molecular simulations and experimental data, if I really want to translate this to real data, I need to be sure that I can really assess the quality of the materials properly in a systematic way. And what is the typical way? Well, if you work with these porous materials, the typical technique is you have a nitrogen isotherm at 77 Kelvin. You can use different equations to characterize and to quantify different values. And the typical one is the use of the BET equation. BET was not developed for microporous materials, but almost any paper will include this figure. Otherwise, people will say, well, you need to include the surface area of the material. A microporous material surface areas are a little bit strange ideas, but it has some analogy and it looks like a surface area. It's a porosity at the end of the day that we can really explore. If I take one material like H+1, you can say, well, it's very easy because I just need to fit BET probably into this range of pressures. The problem is that if I really look at the isotherm on a semi-logarithmic representation, this is not a typical type 1 isotherm. And what you can really see is a combination of different phenomena taking place during the absorption process of nitrogen. What we know is that we are filling different absorption sites with different energies, and this is why you see all these different steps in the nitrogen absorption isotherm, which is something that you very rarely see in an activated carbon, but it's quite important to highlight for these metalorganic frameworks. That was for H+1, microporous material, for MIL101, mesoporous material, but again, a lot of different issues on the isotherms. If we go to something more complex like NU100, yeah, definitely you can see very, very clear steps. And if you go to something like NU1104, you can see that even on the linear representation, the isotherm has not a typical type 1, type 4 isotherm. It's something a little bit weird, but you have something that is increasing slowly again and again. So we said, okay, how can we analyze this problem? And what we decided was to collect 18 materials. We measure in our labs the absorption isotherms, and we send the data, not the materials, the data, the isotherms already measured in our lab to 60 international laboratories. We set them and we say, can you calculate with this equation, with this data, with this absorption isotherm, can you measure the BET area? Can you apply BET area in the best way you can think of? And for some materials like the H+1 that you can see here, most of the people were giving similar results, no problem, some deviations, but most of the people were fairly clustering around specific values. But then we were going for more complicated isotherms, and then you can see this for a COF, covalent organic framework, a lot of deviation. And then if I go to this material that you have here, you look at this dispersion of data, okay? This is the results from 60 different labs. And you can have materials, labs that say, with the isotherm you sent us, we have 2,000 square meters per gram. And another lab said, with the same isotherm, exactly the same data, we measure 9,000 square meters per gram. And this is important because if I'm trying to publish a new material, if I'm saying my material has 9,000 square meters per gram or my material has 2,000 square meters per gram, is quite important. Okay, this is an important question. We need to have something which is highly systematic. So we said, well, fine, we have a problem. We are going to offer a solution. And basically, we created a piece of software that is able to calculate the BET area and is not ambiguous anymore. We have some criteria. This goes beyond Ruckerol criteria that were defined some years ago. And basically, you can see these orange points here. This is the data that our code is giving as a result. And I'm not describing this in detail, but all this is really available in ChemArchive. We have the preprint of the struct of this publication with all the labs that have been involved. This is what looks. This is the output file that we can really get, and we end up with a final value. If somebody is interested, this is quite important. You can really go to this website. You can really have the executable for Windows, Linux, Macs, doesn't matter. And if you have any simulated or experimental absorption isotherm, you can use this software to calculate automatically what is going to be the BET area. So if you are using nitrogen isotherms and you have questions, this is our recommended way to go. Fine. What about the deterministic prediction? I didn't forget about this. You remember I wanted to have the descriptors, surface area, pore volume, pore size, density, composition, and I want to know if I can really predict this quickly. Monte Carlo simulations here, and the solution to this question about the deterministic predictions goes through the machine learning algorithms. Basically, you can see the comparison. This is the training. It took 3 weeks to get the Monte Carlo simulation, but then we trained the model very quickly, and now we can do the testing. In 1 single minute, we can analyze 1,000 materials, so less than a second per material, to be able to understand what is going to be the storage capacity for oxygen or any other gas. This is something that we are including into the software from the CCDC, and this is something that people should be able to exploit in the future as well. Can I use these materials in industry? Can I really extend all these simulations into the experimental data? You have seen the results of the comparison between experiments and simulations. Fine, this works very well in the lab, but still for industry, we have this next question, and I'm just going to finish with the next couple of slides. What am I going to be able to do with a powder? I cannot use a powder in an industrial setup. A powder will have a huge pressure drop in a system, so at the end of the day, you need to save this into some pellets, and there are different ways of doing this. You can use high pressure, you can use a binder. And what is the problem? The problem is that you remember I was telling about MOFs and saying that mechanical properties was a big thing. They don't have really good mechanical robustness. So if we try to pelletize this and we apply very high pressure, we collapse the porosity of the material. We have thousands of square meters per gram, but as soon as we try to pelletize these structures, we collapse, we destroy all this porosity. We can also use a binder to be able to not to use so high pressure. This works really well, but the problem is that we cannot densify the materials too much. If we try to apply very high pressures and densify the materials, we go back to the previous problem, we collapse part of the porosity. We wanted to develop something that was a new pathway for this shaping. We wanted to have 100% MOFs. We didn't want to apply any pressures. We don't want to. We want to have big bodies, small bodies. We want to have something which is very robust. And now we want to have something with very high porosity, but also very high density. We want to densify this powder that we were having here. And this is the results that we have with these materials. We have this beautiful glassy look material, but they are fully crystalline, fully porous materials. And this is something that, as was said in the introduction, this is something that we are exploiting with our spin out in material. This is the comparison of the powder and the monolithic material. This is the nitrogen isotherms, no difference on the gravimetric point of view, but if we go to the volumetric, the density of the monolith is 3 or 4 times higher than the density of the powder, and therefore the uptake is much higher. This is amazing because now we can really use the data that we are getting from the molecular simulations, because now we are going to have a density which is real. Is the density of the monolith is very similar to the single crystal density of the powder. Whereas in the powder, you have this density plus a lot of void space between the particles, and therefore really fraction of the original density of the single crystal. To show this idea, this is something we published a couple of years ago in Nature Materials for methane storage, just experimental data, no simulations here. This is the Department of Energy target, and this is the pressure. So we try to compress the gases, and this is the best material that we were able to find in the literature, including activated carbons, metalorganic frameworks, anything. This is a material from Professor Omar Farha, HCUS1, very far away from the Department of Energy targets, but extremely high capacity for methane storage. They said, well, this is for the powder that you press with the hands. They try to densify this using tetones, and because they are able to increase the density of the powder, they are able to increase the volumetric capacity of the material. 2 tons is not very high. They tried 5 tons, and this is the problem that I was describing in the previous slide. The mechanical properties are not amazing. At 5 tons, you collapse part of the porosity of the structure. This is not good. In our case, the monolithic material was able to have a higher % improvement versus the powder, and we were able to reach the DOE target for the first time. So really happy, as I said, something we are exploiting with in material. The idea is that we have the synthesis of some primary particles, we have a gelation process to synthesize the material, and if we dry this very quickly, we end up with a powder. But if we have a very mild drying conditions, we will end up with these very dense monolithics that you can really see here on the right. And we have been able to extend this to any MOF that we have been working with. We can also use this with covalent organic frameworks, and we can create some macrostructures out of all these different materials. We can also develop different porosities, so we can see using SAX data these different possibilities. So we have seen that we can create different domains, and we can see the existence of some additional mesoporosity in these materials, which is what you can really see here in this representation. At the end of the day, we are going to be able to have materials that we can translate from the simulations to the experiments. Going back to the previous questions, the first one, can we define a deterministic prediction for the material's performance? Yeah, I have answered this question using machine learning. We can really have something which is very fast. And now, if we know the properties of a new material, we will be able to predict the performance without running any Monte Carlo simulations. In 1 second, we will be able to tell you what is going to be the performance in any application that we have trained the models for. And the second question, can we translate these predictions to real materials and applications at scale? The answer again is yes, and this is where we work with these engineered porous nanomaterials or molecular sponges, and we like to call these monolithic materials as MOFs version 2.0, because this is something that can really translate all the volumetric capacities that we have been predicting in the lab or with the computers about these materials, but now using real densities, not the single crystal density, the theoretical density, but the real density of the materials we have developed. A lot of different applications, a lot of different possibilities with these materials. Just to finalize, I would like to say thank you to the people that have been working in these different ideas. Obviously, these are the ones who are really creating all the science these days. A lot of collaborations in Cambridge, but also outside of Cambridge, including Limerick. So thank you all. Thank you, the funding bodies as well, and all you for your attention.
Thank you, Professor, for your nice talk. Very clear, very inspiring for the possibilities with the porous material. I don't know if there's any question. I imagine there would be some from the audience. Is anyone brave enough to make the first question? No one is brave. Oh, yes.
I can be brave.
Hi, Hugh.
Matteo. Hi, Matteo. So I think it's probably an easy question for you to answer. In terms of the material where you showed that it compressed compared to the powder and the gas uptake there, does that suggest that the surface area of your material isn't so important in terms of determining the uptake?
The surface area is very important, but it's also very important the density. So it's the mix of both components. We can really go
to that slide particularly I was thinking of, yes.
Yeah, so this is for C8. That was the first monolithic material that we published in 6 years ago. This is the BET area. I mean, the BET area, we collect this from this region, from the nitrogen isotherm. Okay, we apply this, and if we try to calculate the BET area, just looking at these two isotherms, we will see very similar values. There is no difference almost in surface area between the powder and the monolith. The difference is that we transform these isotherms, and if you want the BET area, into this volumetric representation. Here is cubic centimeters of gas per cubic centimeter of Metalorganic Framework. We are multiplying every single point here by the density of the powder and the density of the monolith. So is the surface area important? Yes, it is very important, but also the density. And this is the big difference. Most of the times in the literature, you see people calculating volumetric capacities or volumetric surface areas by multiplying by the theoretical density of the powders. And this is the single crystal density of the materials, what you can really get from crystallography. But this is not correct, because obviously the powder has a lot of interstitial space between the particles, and even if you have a pellet, you will have a lot of macro porosity, a lot of dead volume that you cannot really exploit. The opportunity with the monolithic material is to be able to develop not only microporosity, but also to densify all the particles so we don't have any dead space between the material.
Great, thanks very much.
There's a question in the chat. Navin Kumar, it was really nice talk. You mentioned that 3D networks have higher uptake than 2D that was obtained from simulation. Is it always true?
The short answer is no, it's not always true. You can see the representation here. You can see every single sphere, every single point is one metalorganic framework. So you can see that on average, this is what we are trying to represent here. On average, 3-dimensional porosities will have higher uptakes than 1-dimensional, but at the same time, you have a lot of MOFs that will have higher uptake for hydrogen, 1-dimensional higher than the 3-dimensional. Okay, these materials, for example, are going to have higher capacity than all these ones that you have here. This is what we have observed also for hydrogen. For other applications, you can have something completely different. If we are dealing with selectivity, many times 1-dimensional networks could be quite beneficial, sometimes because they tend to form more narrow channels, and narrow porosity is what you really want to develop for selective applications. It all depends. It's a lot of different possibilities, and it really depends on the kind of the family of materials you are looking for and the specific application you are looking for.
More questions from the chat. Do you observe any difference in sorption kinetic between powder and monolithic material?
Yeah. If you go to the supporting information, this is one of the questions that we were asking in supporting information of the Nature Materials paper that we published in 2018. We have information about the calibration time. And in the powder, we have a calibration time within a minute for the isotherms at the lab scale, obviously. With the monolithic metalorganic frameworks, we have in 2 minutes. So it's a little bit slower, but still it's pretty fast. That was for that was for methane absorption. And it also depends on the different applications. So in some cases, we have seen that some monolithic materials, they have extremely slow kinetics, and then we just need to engineer them in order to create some additional mesoporosity or something that will open the porosity, the connectivity a little bit more, and this helps to improve the kinetics. Obviously, this will also have an impact on the density of the materials and the volumetric capacity, but there is a balance between all these different properties and possibilities.
I want to add something. Would the gelating agent affect this material? And would that be like the next topic? Start investigating the gelating process in order to increase the kinetic. If you want to increase, sometimes you don't want to increase the kinetic. If you have a cylinder full of hydrogen in a crush, you don't want the kinetic to be, for releasing it to be that fast.
Yeah, I mean, at the end, it's an engineering problem. We can really play with the variables, and we have seen different ways of playing with the porosity profile to be able to optimize the properties we are looking for.
Another couple of questions from Vasant. Thanks, David, for the nice talk. If we need to use MOFs as a storage material, is there any way to synthesize MOF monoliths that match the size and the fuel tank? So again, can you make the monolith the shape of your tank?
In principle, yes, I think it's possible. Or if not, you can really try to optimize quite a lot. And this goes beyond the material engineering, and this goes into the design of the tank. And this is a really critical question. So if you really want to have a tank, that's not a question you should ignore. because you need to think about kinetics, you need to think about heat management, you need to think about all the practicalities of really developing a system with these characteristics. Is it possible to grow a MOF that big? We have seen some very big monolithic materials created with some of the approaches we have. So it is possible in principle, yes. You need to take into account also the fact that kinetic limitations could be an issue. But again, this is a problem that you can also solve if you really understand what you need to do.
And finally, because then we have to go, a question from Mei Lee, a PhD student here at the Bernal. Is it a couple of advices? You enter a different realm. You can take the responsibility. It is possible to scale up to scale it up in some industrial applications. How about the yield and amount of porous material from one batch of synthesis? How can we control the pore side?
Pore size.
Size. Oh, yeah, must be a touch. Yeah.
So with the first question, yeah, this is what Immaterial, the spin-off company we have, is doing these days. We are almost there on 1 kilogram production per day, and in the next few months we will be able to have some multi-kilogram production per day. So we can produce these monolithic materials at a scale with industrial processes. And this really helps us to obviously create these materials for different clients and the different applications we are looking for. In order of well, talking about the yield or amount of porous materials from one batch of synthesis, it really depends on the materials. We have yields that are pretty high because we try to optimize the synthetic processes, and we also try to maximize the amount of solids that we have in order to minimize the amount of volume. There is a lot of research on this area. It's an important question, obviously, but yeah, we try to pay attention to these materials that are cheap to produce, but are also extremely efficient in these applications that we are looking for. About how can we control the pore size? We have obviously the microporosity, what we call the intrinsic porosity, which is given by the crystalline structure of the material. And on top of that, we have the extrinsic porosity, which is the additional porosity created between the crystallites or defects included in the material. We can include crystalline defects, we can include mesoporosity. Sometimes we find this by chance. When we have this situation, we start playing with the different synthetic conditions in order to be able to tune this existence of mesoporosity. We had a paper that we published in Nature Communications about a couple of years ago on UIO66 materials. So if you are interested about how to tune this mesoporosity, you can have more details over there, but it's playing with the synthetic conditions of the monoliths.
Okay, thanks, David, for your nice answer to these questions, your kind answer to these questions. With this, I don't want to take any more of your time and to take advantage of your kindness. I want to liberate everyone to go to lunch. And again, thank you very much for this great talk, and hope to see you in person and maybe to host you in person as soon as this situation changes.
Yeah, thank you very much for the opportunity to present. And yeah, thank you, all of you, for listening.
Thank you. Bye.